Second element of group 16 is sulfur, just below oxygen, twice heavier than oxygen. Again, has 2 valence electrons on s orbitals and 4 valence electrons are on 3p orbital. Sulfur can make diatomic molecule in gaseous phase, but solid sulfur makes a large number of single-bonded polymeric molecules with composition of S6, S7, S8, 9, 10, 11, 12, 13, blah, blah, and so on. There are plenty of different structures like that. It forms beautiful transparent yellowish crystals, all of them. It makes hydride, H2S, which is stable, very toxic, smells, reacts with oxygen, burns in oxygen to make SO2, but when carefully burned, it will make sulfur and H2O. When bond-on angle in water is almost tetrahedral, 105, a bond angle in H2S is closer to right angle, 92.5, and in H2 selenium actually it will be exactly 90. The old-fashioned explanation was 3d orbitals somehow playing a role here. It's nonsense. There is no 3d orbitals in sulfur. The highest is 3p. But in fact, there is simply smaller interaction between HS and HS bond. They are weaker. Distance between hydrogen and sulfur is larger than in H2O because sulfur atom is much larger. So repulsion between these two bonds is much smaller and they can come closer, being repelled by lone pairs. There are 2 lone pairs around oxygen, sulfur, and selenium atom in each of these molecules. There are plenty of different sulfides that make H2S. For example, iron sulfide reacts with hydrochloric acid to make aqueous iron chloride and H2S gas. Easy way of making H2S in lab. Again, H2S can make sulfur. H2S can react with many metal salts to make sulfides like PBS, black like this, and appropriate acid. S2- sulfide ion does not exist in water. It instantaneously reacts with water molecule to make hydrogen sulfate and hydroxide, so the solutions will be basic. This reaction is exactly identical to the reaction of oxide. Most of elements of minerals on this planet are oxide, but there is enormous group of sulfide minerals as well. Many of them are brightly colored, and that's why they are interesting and were known humans for millennia. Very beautiful red pigment, cinnabar or vermilion, this red. There is old Chinese carved artifact made of vermilion. It's fantastically toxic, but very beautiful. Galena, lead sulfide. Pyrite, iron disulfide, cubic like this. Sphalerite, we were talking about it, colorless. Or pigment, again we were looking at it, it's orange or red. Stibnite, chalcopyrite, this one. So there are plenty of beautiful sulfides. They have their specific colors, and they all are insoluble in water and form very large and very interesting group of minerals. Sulfur-sulfur bonds exist in polysulfides. So like in peroxide, you can make HSSH molecule and longer molecules that you cannot make with oxygen. Polymeric molecules with multiple sulfur-sulfur bonds. This distance is very large. Sulfur-sulfur bonds are very important in nature. They form connections between protein bands. You can connect two sulfur-containing amino acid with sulfur-sulfur bridge. They also exist in such common thing as rubber. Sulfur reacts with oxygen directly on air to make sulfur dioxide. The electron formula for sulfur dioxide will be exactly like for ozone. A little surprise because they are this sulfur and oxygen of the same group. So you have sulfur plus and oxygen minus. 3 bonds here, 1 bond there. Sulfur dioxide molecule is bent, reacts with water to make H2SO3 molecule. Now it reacts with bases like sodium hydroxide to make sulfide ion. Here, and there is lone pair, so sulfide, contrary to carbonate. Carbonate would be CO3, but it's flat. Here you have lone pair. Sulfur is an oxidation number 4, so you have lone pair here. And structure is triangular pyramid. You can further oxidize sulfur to make SO3 molecule, sulfur trioxide. In gas, it's flat. This reaction is fantastically important for making sulfuric acid. So after we burn sulfur to SO2, we can continue reaction, but it will require vanadium catalyst and high temperature to make SO3 gas. So SO2 plus O2 to make SO3. Now, SO3 gas is absorbed by contact with sulfuric acid, and then the sulfuric acid is diluted to make liquid sulfuric. So the hydration reaction will be like this: SO3 plus H2O, H2SO4. This is in gas phase. So when you condense it, you can make liquid. When you put SO3 and crystallize it at low temperature so that it makes beautiful colorless crystals that have trimeric structure, S3 or 9, like this. This molecule does not exist in gas phase. Sulfuric acid, H2SO4, we already know that, can be deprotonated. It's famously strong acid. When you have pure sulfuric acid, it's very different from solution in water. First, it still dissociates by itself to make protonated form, H3SO4. So 3 oxygens are protonated, and monodeprotonated form. This sulfuric acid can dissolve some SO3 to make oleum, the word oleum meaning oil, or other words fuming sulfuric acid, H2S2O7. It's again different compound from H2SO4 with fantastically strong acidity. In sulfate ion, you have 4 identical bonds, and these can be described by 4 covalent bonds plus ionic attraction of negatively charged oxygen atoms and positively charged sulfur atoms. Lewis structure will predict +2 charge on sulfur and -1 charge of oxygen. The real charges, of course, are much smaller, but still there is very significant element of electrostatic attraction between positive sulfur and negative oxygen. Sulfates are all highly soluble in water. Exceptions are calcium sulfate, strontium sulfate, barium sulfate, all of them are second group, and lead sulfate. You can replace one oxygen in sulfate with sulfur, making thiosulfate, beautiful colorless crystals. Thiosulfate reacts with iodine to make sulfur-sulfur bridge tetrathionate. That's the reaction that is widely used in analytical chemistry. Sulfur makes compound with halogens. Only fluorine will make compound with sulfur in oxidation number +6, SF6. This is a partially covalent, partially ionic compound. Again, there is no 3d orbitals, like somebody claimed. Now, sulfur can react with chlorine to make S2Cl2 chloride, and further to make SCl2 chloride. There are compounds with bromine and iodine as well.